Okay, we're starting on Chapter 35, Interference, this week. And just before I go on about that, the homework problems for this particular chapter are numbers 4, 16, 21, 31, 33, 39, and 79. I'll repeat. Homework problems are 4, 16, 21, 31, 33, 39, and 79. Of course, those are due on Thursday, and Thursday is also the day when we're having the test over chapters 31, 33, and 34. So if you have any questions about any of that, just shoot me an email. But anyway, let's talk now about interference. Light, as we know, is a wave. Well, it has wave properties. It also has particle type properties too. But in the three-dimensional transmission of waves, including light, you can also usually predict what is going to be taking place by Huygens principle. And that is all points on a wavefront serve as point sources of spherical secondary wavelets. After a time t, the new position of the wavefront will be that of the surface tangent to these secondary wavelets. And figure 1 shows you what they were talking about there, what happens in a vacuum. Now, where this becomes interesting is when you have light going from one type of a medium into a second type of medium, or through several other ones after that. The refraction that occurs at an air-glass interface is portrayed here, and the wavelength on the glass is smaller than that in the air. And so what you see is that you are getting a bending type of activity, and it becomes more pronounced as you go through that. And it will continue on like that. So you have 3 separate stages here as it goes through there. And it continues on other stages until it gets out to the other side. So the refraction of a plane wave in an air-glass interface is shown here. And the wavelength in glass is smaller than that in air. And for simplicity, the reflected wave is not shown. Parts A through C represent 3 successive stages of refraction. So that at this stage right here, only one has started to refract. Here, this one has also started to refract, and you're just getting to, so you see that this point right here. Okay, so both of these are refracted. This part is not. And by this point, all 3 of these are being refracted. So the law of refraction can be derived from Huygens principle by assuming that the index of refraction for any medium is, and this is the wavelength, this is the refractive index, this is the speed of light, and this is the light in the new medium. And the wavelength L sub n, lambda sub n of light in the medium depends upon the index of refraction n in this equation. So that this wavelength, the new wavelength, once it reaches the how it behaves in that medium, this is the wavelength in vacuum, and this is the index of refraction, and this is the new wavelength that you have in that material. So let's do a checkpoint on that. Now, this figure right here shows a monochromatic ray here coming in at A, and it's going into one interface through one type of medium here, another type of medium here, and then back into A. Okay, and so rank the materials according to the speed of light in them, with the greatest first. So you see this has a fairly large refraction here, doesn't it? And this right here has less than this, and this has less than this one. So what that means is that this must have the greatest speed of light. This would have the next speed of light, and then this would have the lowest speed of light in that medium. Okay? So the fact that this is bent so much means that this has the greatest change in this, and therefore the greatest speed. Now, here's another one. You can look at that same type of concept. You have light waves, rays right here, of the same wavelength and amplitude, and they're initially in phase. If 7.60 wavelengths fit within the length of this material right here for the top material, and only 5.50 fit through this one right here, which material has the greater index of refraction? Okay, so what that means is that the top one has to have the greater index of refraction because it has many more wavelengths fit into it. It's the faster one. Okay. If the lasers are angled slightly so that they meet at the same point on the distant screen, will the interference there result in a brightest possible illumination, a brighter intermediate illumination, a dark intermediate illumination, or darkness? And the answer there is that it would be bright intermediate illumination, right? The phase difference is 2.1 wavelengths, 2.1. So it's not the most, but it is still fairly bright. So let's go at practical exercise here. This is problem number 1 at the end of the chapter. And you've got a light wave along ray R1 here, reflected once at the mirror and coming back. For R2, what you've got is you've got a little tiny mirror here, right? And so it's going to go up to this reflection, to here, the back again, and back out again. Okay? And this, where this is located, is at this point L. So distance L from this initial large mirror. Okay? So the waves have a wavelength of 620 nanometers and are initially in phase. What's the smallest value of L, right here, that puts the final wavelength exactly out of phase? In other words, the difference would be pi, right? With the tiny mirror initially at the value L, how much farther must it be moved away from here, okay, to put the final waves out of phase? So the fact that this R2 reflects 2 additional times has no substantive effect on the calculations, since 2 reflections just amount to 2 lambda over 2, or lambda phase difference, which effectively is not a phase difference at all. So it's no substantive difference in terms of phase difference. The substantive difference between R1 and R2 is the extra distance traveled by it. Okay? So R2 to be half the wavelength behind R1, that means 2L, 2 times that distance since it travels it twice, is lambda over 2. So that lambda equals lambda over 4. And since lambda is 620 nanometers, dividing that by 4 gives you 155 nanometers. And destructive interference will again appear if this is 3/2 lambda behind the other wave. So this is 2 lambda prime for this new location. And this is 3 lambda over 2, this factor right here. And so that would be 465 nanometers, and the difference between them is 310 nanometers. This next practical exercise is problem number 5. And here what we're doing is we've included in here this table 33.1, which has several different indices of refraction. Because what they're asking is a very simple question. How much faster in meters per second does light travel in a sapphire than in a diamond? And you have sapphire right here of an index of refraction of 1.77, a diamond of 2.42. And so for any of these different materials, for the different indices of refraction, you can determine how much faster it's going to be going. So the index of refraction for a sapphire is 1.77. For a diamond, it's 2.42. And the speed is the speed of light divided by the index of refraction. And so the change in the velocity between the two is the velocity of the sapphire minus the velocity of the diamond, which means it would be C times 1 over the index of refraction for the sapphire minus 1 over the index of refraction for the diamond. Substituting those values in there and using 3.00 times 10 to the 8th meters per second for the speed of light, you actually end up with something a little different than what they have. This one is correct. This is 600 and sorry. This is correct. This is the 0.565 minus 0.413 times that value, and the slightly different 4.56 is what I got instead, and that's in meter times 10 to the 7th meters per second. So because the difference that I obtained up here was 0.152. Continuing on, practical exercise number 3, and this is problem number 8. This is the one where I had quite a few changes from them. 2 light pulses are sent through layers of plastic. Here you've got 4 layers of plastic with these 4 different indices of refraction. Here you have 3 layers, but this one is twice as thick for this refractive index of 1.59, and these are the refractive indices of the other ones. Which pulse travels through the plastic in less time? And what multiple of L over C, the length over the speed of light, gives the difference between the transversal times of the pulses? So taking times T1 and T2 takes their pulses to travel through them. T2, L over C times this over this value, L times C over this index of refraction, L divided by C divided by this index of refraction and this one. So each of these would be converted into the numerator up here. And so if you add 1.55, 1.70, 1.60, 1.45, you get this factor right here, 6.30. And so it's going to be 6.30 L over C. For T1, this is where there's a big difference. First of all, it's 2L up here, right? 2L divided by this number right here, and L divided by C times, and so this would be L times 1.65. This would be L times 1.56 divided by C. So the number that I have here is 6.39. If you actually had the 3 times this instead, it would have been well over 7. So, but the fact is that the conclusion remains the same. Pulse 2 up here is much faster, travels in less time. This is 6.30. This, whether it's 6.33 or 6.39, would be much slower than this one. Then you have here the difference between these two, and it ends up being 0.09, not 0.03. Okay, so you can do the math on this, and remember this is a negative on here. Next we'll talk about Young's interference. Along with Huygens, that's one of the major different equations in this chapter. And essentially what you're talking about here is what happens when light passes through a slit. Diffraction occurs, and what happens is it bends to a certain degree. And the closer this spacing is, the smaller A is, you'll see that the curvature becomes greater and greater. Okay? So the greater the diffraction, this is why you get a diffraction here. The diffraction pattern exists when you have another set of slits associated with this. For example, this figure gives you the incident wave, and you have your diffraction here. When you have these 2 additional ones at another location further from here, you'll get constructive and destructive interference as you go along there, with a maximum here, with an absolute minimum in between. Okay, so the diffraction of the light by these 2 slits sends overlapping circular waves into the region beyond the screen B. And I think we will have to stop right there.